In this video, we will understand in detail how a 7-segment display module is interfaced with an 8085 microprocessor educational training kit to display the desired combination of alphanumeric characters. Using this, you can display any 3-letter or 4-letter word of your choice too. Why just 3 or 4 letter? Because the display screen which I had the limitation of up to 4 characters only. In the second half of this video, we will also get to see a demo video clip in which I will be doing things in a laboratory, in a lab, where you could see the 7-segment display interfaced with an 8085 microprocessor kit and how I would be feeding the code, the customized code for the characters of my choice. So to start with, what all do you need? An 8085 microprocessor kit, a 7-segment display interfacing module, a 26-pin FRC, which is flat ribbon cable, a 2-wire power cable, and a regulated power supply. Now for someone who would be trying this for first time, these words might look frightening, but these are not that of a complicated thing. For example, regulated power supply can be just the power supply at your house. The power supply at your house, which you get through those sockets, is regulated because had it not been stable, then many of your electronic devices might have been damaged by this time. And this 26-pin FRC, a flat ribbon cable, is just this. So our device uses common anode logic. Can you see this plus 5 volt disconnection? So this is the positive voltage supply. In the common anode configuration which we are using, the positive side, the anode of all internal LEDs, all these 7 segments along with this decimal point dot, is tied together to this single plus 5 volt point. They all share a common positive connection, and when you turn a segment on, you provide a 0 volt, a ground signal to its individual pin. So the main display is made of 7 LEDs arranged in a specific pattern, which is the figure 8. These 7 bars together make the figure 8. You can light up different combinations of these LED segments to form any digit from 0 to 9 and other alphabets as well. And can you see these 8 resistors, each of 220 ohms? Why are these here? LEDs are sensitive to current. Connecting them directly to power will draw too much current and burn out. So the resistors here limit the flow of electricity to a safe level to protect the display. Now coming to the interfacing part, on the left there are 8 switches connected to the 0 volt ground. In reality, in our 8085 microprocessor kit, we do not have these switches, but we have input output pins. When the microprocessor sends a logic 0 to a pin, it acts like closing the switch. So this will complete the circuit and electricity will be able to flow from this plus 5 volt source to the segments, to these resistors, and down to the ground, making that particular segment light up. Now if you want to display a particular character, you will have to determine which segments need to be on. For example, if I want to display the small letter O, then I would like to light only C, D, E, and G and turn off B, A, F. So for this, the microprocessor will have to send a 0 to the pin C, D, E, and G and a 1 to B, A, and F. So electricity current will flow through this path C, D, E, G, and you will see small letter O glowing up here. We use multiplexing here to save connection pins. All digits in a multi-digit display share the same segment lines. The processor turns on only one digit at a time, and this happens very quickly, quicker than what we humans can perceive as two different events. Switching digits at a high frequency, which I have known to be more than 50 hertz, we cannot see it flickering if you switch it so fast. And because of the persistence of vision, all digits appear constantly lit. And this method is highly efficient. It reduces the number of required pins from 32 down to just 12 for a 4-digit display. Now, you must have noticed by this time that we are using LED and not LCD. Our 7 segment is using LED and not LCD. What is the difference? The fundamental difference is in the physics involved behind the working of both of these. So LEDs use electroluminescence while LCDs use electro-optical modulation, which is a totally optical thing, an optical phenomena. So in electroluminescence, in LEDs, we have semiconductor material. You can think of a PN junction that an LED has a positive p-type layer and an n-type, a negative layer. And we know electron recombination. When electricity runs through this semiconductor, this PN junction, electrons from the negative side jump across the junction to fill holes on the positive side, and then photons are emitted. Because electrons will be dropping from a higher energy state to a lower energy state, they will release their energy in the form of photons. And the specific band gap energy of the semiconductor material will determine the wavelength of the light produced. Because if you fix the wavelength, you will fix the color. In LCD, we have liquid crystals. We know the full forms, right? LED is light emitting diode that emit their own light. LCD are liquid crystal displays. They have liquid crystals which are somewhere in between a solid and a liquid state. They work on the principle of polarization of light. So an LCD has two polarizing filters which are perpendicular to each other. So the light which passes through one filter will then be blocked by the second filter. So liquid crystals naturally align in what I can say in layman terms, a twisted spiral. Light passes through these crystals. Crystals guide the light and twist it by 90 degrees. So it passes through the second polarizer. And when an electric voltage is applied, the liquid crystal molecules straighten out, they untwist. And in the straightened state, they cannot twist the light the way they were doing before. So the light hits the second polarizer an at an angle such that it is blocked, creating a dark area, which you see as a segment, which you see as a pixel in LCD screens. This is also the reason why LCD use very low power and LEDs use higher power. So LCDs are used in applications where you want to consume low powers, let us say battery run devices. And setting up this is quite simple. You connect the LED module with your microprocessor to specifically to the 8255 port of your microprocessor using this 26-pin FRC. Once this is done, you connect plus 5 volt and ground from the kit to the module using the 2-wire power cable. Then you enter the assembly program starting from this memory location 2000. H is just to tell you that this is a hexadecimal number and not a normal not a normal decimal or not a normal octal number. And finally, we input the hexadecimal data for characters starting from the address 2100 and execute it, which is the fun part I've been talking about. This is the code. I have divided it into two parts because the entire code will not be able to fit on one screen. So firstly, we have the initialization thing starting from the address 2000. So we set up the hardware and clear the display. We load the accumulator with ATH and output it to port 03 to configure all ports of the 8255 as output ports. Then the code initializes a counter in register D to perform a blanking operation. This ensures the display is cleared of previous data before the new word is shown. This part toggles the clock signal by sending 00H and then 01H to the appropriate port to trigger the hardware. Starting from here, from this address 2016, we start loading characters, not the actual final output which you want to display on the screen, but you start preparing the data that will actually be displayed. As in, like you load HL register pair with 2100, which is the starting memory address where your character codes will be stored. And then register C will be initialized to 04 to count 4 characters. Then register B will be initialized to 08H to count the 8 bits required for each character. The instruction move A, M brings the first character code from memory into the accumulator. Starting from the address 2021, we have the serial data transfer thing. Because the display module receives data bit by bit, which means serially, it receives data serially, the code must rotate the character data. The clock signal is initialized to a low state. Using RLC and or RAL, the code shifts the bits of the character code. Each individual bit is sent out through port 01. This is the output port. The clock is made high to lock that bit into the display's shift register. Then the code decrements B, the register B, and loops back until all 8 bits of the current character have been sent. Starting from the address 2033, we have the delay and character loop. So the code calls a subroutine labeled call delay and it creates a 0.5 second delay, a pause. This delay allows the human eye to perceive the character correctly as they are shifted. And then the code increments to HL pointer to the next character in memory and decrements the character counter, which is C, and repeats the process until all 4 characters are displayed. And once finished, the RST5 instruction stops the program and returns control to the kid's monitor system. Next, you have the character data entering part starting from the address 2100. So the specific patterns that you want to display will be determined using the hexadecimal values which you enter here. How it happens exactly? For this, let us jump to the demo video.
So today I am trying out a 7-segment display module on this 8085 LCD kit, and I am trying to write different words using it. And just to show you how to enter code and what will it display, I simply so I start entering the code for respective letters from this address, and it goes like this.
You can see 2100, although it is not that clear, but this is the starting address from where we write the customized code.
And it goes like this: A1, C0, C0, A2. And then I write G200, which is the starting position from where the code to activate 7.
Please note it is 2000. It was my mistake that I pronounced it as 200 in the video, but it is 2000. G2000.
Segment was added, and then I press shift plus 4 and it displays GOOD, good. Now how this works is this.
You can see this is the 8085 microprocessor kit, this wooden box. This is the FRC cable of which I also showed you a picture. This is the 7-segment display module, and this is the 2-wire cable which I was talking about, which is used to give power supply to the module from the kit, and the kit gets its power supply from this.
When I addressed A1 on the first address 2100, it went to this location. A1 is not for this, it is for this. So the memory address 2100 corresponds to this display 1. Then you can see on the kit here it writes display 2, display 3, display 4. So the addresses 2100, 2101, 2102, 2103 go like this. Now for 2100 I wrote A1 in hexadecimal. A1 is for the number 161, and in binary it can be written like this. And this is the chart for 7-segment display. Now when I carefully observe this number written in binary, then we can see that this corresponds to different LED lights like this: A, B, C, D, E, F, G.
The last one, or the most significant bit here, is for the decimal point, which we are not using for this activity. So whichever part you do not use, you give it a 1. The part which you want to use, that you give a 0. This is why the first bit here is 1.
For this experiment, when I enter 1 for a particular place, then it turns off that line, and when I enter 0, then it turns on that LED. So when I wrote this 10100001, so A and F are turned off, rest all are turned on. So if you turn off A and F, then you get D. Similarly, C0 corresponds to O, and 82 corresponds to G. Now I tried out some other letters when I realized this logic. So if I want to write it in the right opposite of opposite of good, then it would be bad, but that is a 3-letter word. So I will write this, which is a Hindi word, in English because it has 4 letters. I figured it out in the same manner that for B you have to turn off A and F. A and F are turned off, so these are 1, rest all are 0. Similarly, I will have for U, R and A. A is similar, so I have to just turn off D, A, B, C, D, so this will be 1, all other will be 0. And it will correspond to 128, 1248, 136. In hexadecimal, it will become 88. 8 into 16 is 128, plus 8 you get 136. So now to type BURA, I will start entering from here. This so this will go for 2103, the address, and this will go for 2100. This is the first letter, so we have to enter in reverse order. 2100. So I will enter 88, AF, E3 and A3. Now I will execute it again from the same address, G200, shift 4. And you can see it, BURA. If I want to still type in English BAD, then I will have to not use this display, which is display 1, which corresponded to the address 2100. So I have to turn off all the lights for this, which means all the positions have to be 1. 1, 1, 1. All have to be 1 for it to turn off, which is FF in hexadecimal. So here will be FF, then A1, 8883. This I have already realized from the previous course for good and bura. So E2100 will be FF, because 2100 corresponds to display 1, which I have to completely eliminate now. FF means the largest number, which will turn off all the LEDs. FF, A1, 88 and 83. Now I will execute it. G2000 shift 4, and it writes BAD back. That's it. It is a very interesting experiment, and I had fun doing it and realizing how all this works. Thank you.
This was the 7 segment interfacing activity. But this looks more like a toy, right? It does not have any real world applications. It is not used in real world. Or is it? Yes, it is still used outside laboratories, outside the toy world. It is used in industrial meters because it gives you high contrast display. It is used in consumer electronics, and it is used in emergency signals as well because it is simple and it does not consume much of power as if you use an LCD. So it is simple and it is reliable and inexpensive. That's it for this video. Thank you.